In this tutorial, we're going to learn how to analyze an NMR spectrum by focusing on each and every individual signal and learning how to analyze each signal. For example, here is one signal, here is one signal, and here is one signal. And for each signal, we're going to look for three things. First of all, there is where it shows up on the spectrum. Where it shows up on the spectrum is called chemical shift, and we use the symbol delta to refer to the chemical shift. It's also measured in ppm. So this would be 0 ppm, and let's call this 1 ppm, 2 ppm, 3 ppm, so on and so forth. Usually an NMR spectrum goes from 0 to 10 ppm. We're just looking at a part of an NMR spectrum right now. And when we refer to the delta value or the chemical shift, we're referring to where on the spectrum the signal appears. The second characteristic of every signal is the integration. The integration is the area underneath the signal. In other words, saying if you count up the area underneath each of these individual spikes, and you add up that area, you get a certain value. And that value, the integration, the area under the signal, here the area under the signal is this plus this plus this. Here the area under the signal is this. The area under the signal tells you the number of hydrogen atoms giving rise to that signal. So in other words, saying if you have 2H here, and 3H here, and 3H here. So we've got 3 protons giving rise to this signal, 3 protons giving rise to this signal, and 2 protons giving rise to this signal. That's the integration. And the third characteristic of every signal is the multiplicity. Is it a singlet? Is it a doublet? Is it a triplet? Is it a quartet? Singlet, doublet, triplet, quartet, that's an issue of multiplicity. And what that tells you is it tells you the number of neighboring protons. In other words, saying, here we have a quartet. 1, 2, 3, 4. It's a quartet. Here you have 1, 2, 3. This is a triplet. And the way that it works is what we call the n plus 1 rule, where n is the number of neighbors. In other words, saying, let's say you have 2 neighbors. 2 plus 1 is 3, which gives a triplet. So a triplet comes when you have 2 neighbors. A quartet comes when you have 3 neighbors, because if you have 3 neighbors, 3 plus 1 is 4. That's a quartet. So a quartet comes from 3 neighbors. Let's go through each of these one by one, starting with the chemical shift. Let's just give some rules of thumb here. A CH3 group is generally going to show up at around 0.9 ppm. A CH2 group is generally going to show up at around 1.2 ppm. And a CH group is generally going to show up at around 1.7 ppm. We need to add to these numbers when any one of these groups is next to something else. For example, let's say you have a CH3 group next to an oxygen. So oxygen is going to add to the CH3 group. CH3 is normally 0.9, but the oxygen adds plus 3. So this is going to show up at around 3.9. So oxygen adds plus 3. And a carbonyl group adds plus 1. A carbon-oxygen double bond adds plus 1. And by using these rules, we can get through most of the examples that we're going to see. Let's look at this example right here. This carbon atom is a CH3 group, 0.9, next to a carbonyl, plus 1. 0.9 plus 1, we expect this to have a chemical shift of 1.9. Here we have a CH3 group next to an oxygen. CH3 is 0.9. Next to oxygen is plus 3. That's 3.9. What about the following case? This carbon right here is a CH group. CH, 1.7. Next to carbonyl, plus 1. 1.7 plus 1 is 2.7. We expect this to be 2.7. This here would be 0.9 plus 1, 1.9. These effects taper off drastically with distance. For example, if we have something like this. Here you have a CH2 group. CH2 is supposed to be 1.2. It's next to oxygen, plus 3. 1.2 plus 3, we expect 4.2. It's just a rough estimate. It might be at 4.5, it might be at 4.0, but it gives us a general idea of where we expect the signal to show up. Now, this carbon over here is also a CH2 group, but it's no longer next to an oxygen. It's one removed from an oxygen. So instead of adding plus 3, it might only add plus 0.5. And here we have a CH2 group, which is even farther removed. Instead of adding plus 3, instead of adding 0.5, maybe we're just going to add 0.1. Here, you probably don't even feel it at all. So in other words, saying inductive effects taper off drastically with distance, where the plus 3 is really only for the group that is the carbon atom that is directly next to the oxygen. As soon as we move one away, it drops from plus 3 to being 0.5. Also, for example, here, this CH group, we're going to add plus 1 for being next to a carbonyl. But this CH3 is one removed from the carbonyl. So instead of adding plus 1, we might only add plus, let's say, 0.2, something like that. And if you're even further removed from the carbonyl, then it probably won't be noticeable. So these are the rules of thumb we can use for assigning chemical shift. These numbers right here, together with these changes. Next to oxygen plus 3, next to carbonyl plus 1. Remember that there were 3 characteristics of every signal. We've talked about the chemical shift. That's where on the spectrum it shows up. Let's talk about integration. Integration is the number of equivalent hydrogens giving rise to the signal. For example, here we have 3 hydrogen atoms giving rise to one signal. Here we have 2 equivalent hydrogen atoms giving rise to one signal. And here we have 3 equivalent hydrogen atoms giving rise to one signal. So there's a total of 3 signals on this NMR spectrum. And the integration of this signal is going to be 3. The integration of this signal is going to be 2. The integration of this signal is going to be 3. In other words, saying the integration tells us the number of equivalent protons giving rise to the signal. Let's look at the following example. Here we have a tert-butyl group. In other words, saying we have 3 hydrogen atoms here, 3 hydrogen atoms here, and 3 hydrogen atoms here. And all 9 of these hydrogen atoms are equivalent. Here you have 3 hydrogen atoms here. So the NMR spectrum of this compound is going to have 2 signals. One signal, 3H, and the other signal, 9H. Now, it's important to note that integration values are relative. In other words, saying it might not say on the NMR spectrum, when you see these 2 signals, it might not clearly say 3H on one signal and 9H on the other. It might say 1 and 3. Why? Because the ratio of 3 to 9 is 1 to 3. When you see 1 to 3, you need to know that that might mean 1 proton versus 3 protons, or 2 protons versus 6 protons, or 3 protons versus 9 protons. Sometimes it'll clearly say 3H, 9H. Sometimes it'll just give you ratios, and you need to figure it out from there. That's the integration value. The final characteristic of every signal is the multiplicity. And what the multiplicity tells us is the number of neighboring H's. The number of neighbors. And we've already said there's the n+1 rule. So for example, here we have a signal coming from 3 hydrogen atoms. This signal is going to have an integration of 3 because it comes from 3 hydrogen atoms. But how many neighbors does it have? It has 2 neighbors. So this signal is going to be split by these 2 neighbors into n+1, the number of neighbors plus 1. 2 plus 1 is 3. So this signal here is going to be a triplet. This signal here, it doesn't have any neighbors on this side. It has 3 neighbors on this side. n+1 rule. 3 plus 1 is 4. So this signal here is going to be a quartet. Here we've got 3 hydrogen atoms. Here we've got 3 hydrogen atoms. All 6 of these hydrogen atoms are equivalent. So we're going to have one signal. We're going to have one signal with an integration of 6. And the question is, how many neighbors do these guys have? Well, when we say neighbors, we're talking about what are the neighbors of these protons? We look at the carbon that they're connected to, and we move over 1 carbon. We say, how many hydrogen atoms are connected to this carbon? And the answer is none. How many neighbors do these guys have? Move over 1 carbon atom. None. There's no hydrogen atoms here. So these 6 protons have 0 neighbors. n+1 rule, 0 plus 1 is 1, is a singlet. So this signal is going to be a singlet. What about this signal right here? We've got 3 hydrogen atoms here. How many neighbors? We move over 1 carbon atom. There's no neighbor.